Not many are watching these, by the way, so I don't even know why I'm doing it. Okay. So we did horizontal. Now we're doing vertical. And you see what I got on the board there? So I think we'll just do this for a couple days and then call it quits on circular motion. We got lots more stuff to do. We got to get at it. Okay, especially after weeks like this where we got classes that are getting missed. Because believe me, this morning's class isn't the only one that's going to happen this week. Did I hear a chirp? Yeah. Thought the phone was ringing. Or I'm losing my mind. Okay.
What class will be this week?
I'm not telling you. So, at the bottom, as these keys come along, we know they're connected to a lanyard. You know that's a technical word for what the keys are attached to?
No.
Oh, you did? I didn't. You guys are smarter than me. Rope, I don't care, chain, whatever. What's keeping this thing in circular orbit? That tension, right? That's what's causing this circular motion. So there is tension, but there's also weight on these keys, okay? So tension, this is what's causing the circular motion. So this is what's causing the circular force, or the centripetal force is how we call it, right? Centripetal means towards the center. All right, so Fc, here's the formula, is mv squared over r, okay? But down here, if mg were bigger than t, what must happen? It would go that way, but it's not. We know it's still going around in a circle. That means this has to be bigger than that, right? To keep it in this circular orbit. Okay? So the difference there, that minus that, is what is the centripetal force. Right? So it's not just force of friction. There's two forces here. I got two arrows. That's a free body diagram for the keys at the bottom. Now, what about the top? Spins around over here. Which way does weight go? Same, always towards the center of mass of where this thing is, which is there. Now, which way is the tension? It's in the same direction, isn't it? Okay, well, I'm not doing that smaller on purpose. I just don't want it to get all cluttered, but let's just do it again. So that is right on top of the same place, okay? But just so we see it, let me write it there. And they're not necessarily equal in magnitude. Don't say the two arrows are the same, therefore they're the same. Okay, but at the top, what's going on? These guys are in the same direction, aren't they? So mv squared over r is t plus mg. Okay? So let's compare the two tensions. Let's compare tension at the top first. Okay? So T, if I solve this for T, I minus mg to both sides. All right? And what did I put for a mass of my keys? What's a nice number? What's even nicer?
3.
Because I need to put that in kilograms, don't I?
1 kilogram.
Yeah, that's a lot of keys. Obviously, it's not that. But let's just say, okay, for simplicity's sake, let's make a nice number, okay? So 1, what's V? 10, what's my radius? What's a nice radius to have? Sure. 1 meter. It's all got to be kilograms, meters, seconds, right? Minus. So my tension at the top, because this will differ, is what's 100 minus 9.8? 90.2 newtons. So what do we expect it to be at the bottom? tension. Where's this thing gonna break? Yeah, we kind of all said that kind of common sense thing, right? Which means, well, if it's gonna break, the tension should be greater at the bottom. So let's check out the bottom. If I solve that for tension, what do I got? mv squared over r, add mg to both sides, and that's the difference, right? That's minus mg, this is plus mg. So that's still 10 squared times 1 divided by 1 plus 9.8, which is, like, doesn't look like a lot, but that's 20%, isn't it? That's significant, right? So if you, anybody tried to sit in a swing in a playground over here and in elementary and your friend tried to push you right around? No? Didn't quite make it? But, okay, you've been at the P&E, some of you guys? Have you felt the rides? Have you felt it? Like, do you feel the force at the bottom greater than the top, even though the thing might be doing the same speed? Have you been in something like that? Right? Okay. Again, G-forces, I've showed you pictures of people in planes, right? Now this is different because it's talking about blood flow going from your head into your butt. And how do you prevent that? Well, you squeeze like hell, right? I don't want that blood getting away from my head. But the G-forces, the negative G-forces at the bottom, okay, they feel a little more substantial on the top. Kind of different principle, but I don't know. Just trying to connect a couple things here. Okay? So, there's one question. Example 2. At what speed will a 120 kilogram, what's that say? Yeah, it's not master ceremonies, it's motorcycle, bike, and a rider get air? Over a jump, radius 20 meters. Kind of practical question. I'm exaggerating this, but even if that's a tiny little whoop-de-doo, at some point here there is a radius of curvature, okay? And in this case, that's 20 meters. Actually, don't write it right there. Write it over here. Okay? That's the radius of this jump. Okay, we got a nice little Here's Dannon on his chopper. Wearing his helmet, of course. Okay? So, free body diagram for this thing, what does it look like? What's the easy one? Is this guy on Earth? Yeah. Is there gravity? Yeah. Otherwise it wouldn't be very fun, would it? Sit there and spin your tire, nothing would happen. You wouldn't go anywhere. Anyway, whatever. You're on Earth. Why do I complicate things? Any other forces on this thing? Well, okay. Well, yes, but for this question, what does that mean, get air? I haven't explained that yet, but let's say right there, he's not quite at the top, so let's say Fn. There's a normal force, he's sitting on a surface, okay? But what does get air mean? We know what that means, right? That's the fun part. G-forces. That's what life is all about. G-forces, right? Get air, as far as this question is concerned, means what? off the ground, which means Fn, yeah, right? Because the faster this person goes, the more force there, and the smaller and smaller that will become until, woohoo, right? You get your first tricycle as a kid, I mean, what's the natural thing to do? Get it airborne, right? You bet. So at that point, what is the only force here which causes this centripetal force? It's just that. That is the centripetal force. Okay? There's no difference of that. Like we got this, the difference of those two forces is Fc, which is mv squared over r, but that is 0. Right at that point. Just scraping the surface, right? Just came off the ground. So again, the question would probably be, what's the minimum speed, right? Because you know if you go faster than that, well, you still got that, but you get more air, okay? So right at that point, this is what we have, okay? So that's a concept. It's the combination of two formulas. What can I do here mathematically? That's the same m. So GR is V squared. Looks pretty simple, doesn't it? V is the square root of GR, which means on Earth, that's the only factor. Does that kind of make sense? The bigger the radius, the faster you're going to have to go, right? And if there is no radius, if it's just Earth, technically, that's still a radius, isn't it? If I went fast enough, I would get air off of Earth, even without a jump, because Earth is round. If I go really, really, really slow, then my jump's going to have to be like that, right? Tiny, tiny little radius, maybe only a couple inches if I'm on a tricycle. So it kind of makes sense? 9.8 times 20. Take the square root of that. So according to this question, someone's going to have to do 14 meters a second. Is that a reasonable speed for a motorbike? Oh. 50 kilometers an hour? Well, it's obviously doable, right? Okay? 1 to 10. It's to the ground. Well, yeah, good question.